In a laboratory in Colorado, there is a single atom of aluminum being held perfectly still inside a trap made of fields you cannot see. It is cooled to a whisper above absolute zero. It does not glow, it does not move, and it is the most precise thing human beings have ever built anything around. A clock so accurate that if you had started it running at the birth of the universe, it would not yet have slipped by a single second. It was finished last summer, and the very first thing it turned out to be precise enough to check was whether the fixed numbers underneath all of physics are actually holding still. They may not be. Which opens a question nobody quite knows how to ask properly. If the constants are drifting, what exactly are they drifting through? Get comfortable and settle in. Subscribe if you have not, and stay with us tonight, because before that question can go anywhere, you have to see what happened when a laboratory in Oxford stopped timing a clock and started measuring what it cost to look at one. Let's begin. Part 1. The clock that became too accurate. In July of 2025, in a laboratory in Boulder, Colorado, a team at the National Institute of Standards and Technology finished building the most accurate clock that has ever existed. It is not a large machine. It does not look like anything you would recognize as a clock. There is no face, no hands, no pendulum, no ticking you could hear if you leaned close. At the center of it, there is a single atom of aluminum stripped of one electron so that it carries a small electrical charge and held motionless inside a trap made of electromagnetic fields. The atom is cooled to within a fraction of a degree of absolute zero, which means it is barely moving at all. And that stillness is the entire point, because a moving atom is a smeared atom, and a smeared atom cannot keep good time. Held still and cold, that single ion oscillates between two energy states at a frequency so regular that the clock built around it measures time to the 19th decimal place. Let me try to put that number somewhere you can hold it. The previous world record was the 18th decimal place, and that already felt like an absurd level of precision. A clock that would neither gain nor lose a single second across a span of time longer than the universe has existed. 14 billion years, and it would still be right. The new instrument is approximately 41% better than that. We are now measuring time with an accuracy that has no ordinary comparison, because there is nothing in ordinary life that requires it. No train timetable needs this. No spacecraft navigation needs this. Nothing that anyone does with the concept of time on a daily basis comes anywhere near demanding it. So why build it? That question has an answer, and the answer is the reason we are here tonight. Because there is a threshold, somewhere in the accumulation of decimal places, where a clock stops being a device for telling time and quietly turns into something else. It becomes a probe. It becomes an instrument for detecting anything at all that could change the rate at which time passes, or that could change the physical constants governing the atom doing the ticking. Below that threshold, a clock just tells you what time it is. Above it, a clock starts telling you things about the structure of reality that nobody asked it about. The aluminum ion clock in Boulder has crossed that threshold, and here is the part that almost nobody reported when the story went around. The moment this clock became accurate enough to actually matter, it revealed something uncomfortable. It is now sensitive enough to check whether the fundamental constants of nature, the fixed numbers that hold all of physics together, are actually fixed. I want to be careful with that sentence because it can be misread in a dozen unhelpful ways, and getting it right is worth a minute of your time. There are certain numbers that appear over and over in the equations of physics. The fine structure constant is one of them. It determines how strongly electrons interact with light, which is to say, it determines how atoms hold together, how chemistry works, how the material in your body behaves. The gravitational constant is another. It sets the strength of gravity itself, how hard the Earth pulls on you, how tightly a galaxy holds its stars. These numbers show up everywhere. They are the fixed points that everything else is calculated against. But here is the thing about them that does not get said often enough. None of them are derived from anything deeper. Nobody has ever calculated the fine structure constant from first principles. Nobody has produced a theory that says it must be exactly what it is and could not have been anything else. We know these numbers because we measured them. They are written into the equations by hand because that is what the experiments say, and a measured quantity, unlike a mathematical necessity, has no obligation whatsoever to hold still. If those numbers are not derived, then there is no fundamental reason they cannot drift. They could be sliding very slowly, almost imperceptibly, in a way that nobody would ever notice with an ordinary instrument. To catch a drift like that, you would need something so precise that a change in the 14th or 15th or 16th decimal place would show up as a visible discrepancy, which is exactly what has now been built. Not assume, check. So think about what has just happened here. You build the most precise instrument in human history. It takes years. It takes a room full of lasers and vacuum systems and cooling apparatus and people who have spent their entire working lives on the question of how to hold a single atom still. And the first thing that instrument tells you is that the ground underneath physics may not be as solid as you thought. That is where we are starting tonight. Not with a theory, with a measurement, and with a result that does not add up. I want you to sit in that room for a moment before we go anywhere else, because the rest of this is going to move a long way from Boulder, Colorado, and it is worth remembering how quiet the beginning is. Imagine you are standing in that laboratory. It is a room like any other technical room. Grey equipment racks, cable trays running along the ceiling, the low steady hum of cooling systems that never switch off. There are no windows, because sunlight would be a nuisance. On the bench in front of you, there is a vacuum chamber roughly the size of a large cooking pot, wrapped in wiring, and somewhere inside it, suspended in nothing, held by fields you cannot see, there is one atom. One. It is not doing anything spectacular. It is oscillating back and forth between two energy states at a rate so regular that if you set it running at the birth of the universe and came back now, it would still be right. Nothing about the room feels significant. There is no countdown. Nobody's watching a screen with their hands over their mouth. There is just the hum and the equipment and a machine performing the most precise act any object built by human hands has ever performed. And what that machine is quietly reporting back, to the small number of people who understand what they are looking at, is that the numbers underneath everything might not be holding still. Nothing in this video is going to be louder than that room. I want to say that now. This is not a story about a disaster or an explosion or an alarm going off. It is a story about a series of very careful, very quiet measurements that were designed to answer a simple question, and that have collectively produced an answer nobody knows what to do with. And before we can even ask whether the constants are drifting, there is a much more basic question sitting underneath the whole thing, and it is going to turn out to be the hardest question in this entire video. If something is drifting, it is drifting with respect to something. It is changing against some backdrop, and if that backdrop is time, if the constants are moving through time the way a car moves through a landscape, then we had better be very sure we know what time is. We do not. Part 2. What a clock is actually measuring. Before we go further, there is something worth sitting with, and I suspect it is going to be less comfortable than it sounds. What is a clock actually measuring? Not how. We know how. Pendulums swing at a rate set by their length and by gravity. Quartz crystals vibrate when you run a current through them. Cesium atoms transition between two energy states at a fixed frequency. And if you count 9,192,631,770 of those transitions, you have counted 1 second. That is the definition, and it has been the definition since 1967. The how is not mysterious. The how is engineering, and it is very good engineering. The what is missing. When you glance at your watch, you assume it is reading some property of the universe that exists independently of the watch itself, something called time, something that flows, that passes, that cannot be stopped or reversed or set aside. The watch is a window onto that thing. The watch does not create it. The watch reports it, the way a thermometer reports a temperature that was already there. That assumption feels so obvious that it barely registers as an assumption at all. It feels like a description of the furniture of reality. But here is the problem. Physics does not have a clean definition of time that is not circular. Every formal definition either uses time to define time or borrows from everyday experience and dresses it up in mathematics. Newton gave us the boldest version in 1687, and it is worth hearing his actual words because they are so confident. Absolute, true, and mathematical time, he wrote, of itself and from its own nature, flows equably without relation to anything external. There it is. Time as a river that was already running before anything existed to float on it, and that will keep running after everything is gone. It exists in its own right. It does not depend on matter or motion or on anyone being around to notice. For 200 years that was the picture, and it worked so well that it stopped looking like a claim and started looking like common sense. Einstein dismantled it in 1905. That story is well known, that time is not the same for everyone, that a moving clock runs slow, that simultaneity depends on who is asking. We will get to the experiments that proved it, and they are extraordinary. But I want to point out something about that dismantling that does not usually get mentioned. What Einstein replaced Newton's absolute time with is not a definition either. Special relativity, and then general relativity, describe with fantastic precision how time behaves, how it stretches when you move fast, how it compresses near mass, how it trades off against distance in a fixed mathematical relationship. That is a description of behavior. It tells you what time does under specific conditions, and it tells you correctly, and it has never once been wrong in 120 years of testing. But knowing what something does is different from knowing what it is. I can tell you exactly how a currency behaves, how it moves, what it exchanges for, how its value shifts, without ever telling you what money fundamentally is. The description can be complete and predictive and still leave the thing itself untouched. Carlo Rovelli, who has spent more of his working life on this question than almost anyone alive, puts it about as plainly as it can be put. We know an enormous amount about how time behaves. We do not know what it is. Those are not the same thing. And that gap between the behavior and the identity is exactly where the experiments start producing results nobody expected. Now come back to that room in Boulder with me, because the gap reopens the NIST result from a completely different side, and this is the hinge that swings the rest of the video open. Suppose the constants really are drifting. Suppose the fine structure constant today is not precisely what it was 1 billion years ago. That is a genuine possibility, and it is now a testable one, and the unsettling part is not the drift itself. The unsettling part is the question underneath it. If the constants are changing, what are they changing with respect to? Something has to serve as the backdrop against which the change is measured. Something has to be the axis along which before and after are laid out, so that a difference between them can even be stated. And if that something is time, then we are in an awkward position, because the laws of physics are supposed to be the fundamental description of reality, and time is supposed to be a feature that emerges from, or at least sits inside, that description. But if the laws themselves are changing, if the constants have a history, then the laws are inside time. Time is more fundamental than they are. Time stops being a consequence of physics and becomes the thing physics happens inside, which inverts the whole relationship. It means you cannot derive time from the laws because the laws are downstream of it. It means time would have to be the one thing that does not come from anything else, and that is one possible reading. There is another reading which is exactly the opposite, and which we will come to much later tonight, where time is not fundamental at all, but something that appears the way heat appears, not present in any individual particle, only in the collective behavior of enormous numbers of them. Two of the most serious physicists working on this question today look at the same set of experiments and come down on opposite sides of that question. I'm not going to tell you which one is right because nobody knows, and pretending otherwise would be a disservice to how genuinely open this is. What I'm going to do is walk you through the experiments. Because this is not a philosophy video. Every single thing I'm about to describe is a real measurement, performed with real apparatus, published and reproduced. People went into laboratories and ran experiments on time itself, not on theories about time, on time, and the results have been coming back for 67 years now, and each one is stranger than the last. The first one happened in a stairwell at Harvard, and it is so simple you could almost sketch it on the back of an envelope. Part 3. The Clocks That Came Home. Different. In 1959, two physicists named Robert Pound and Glenn Rebka did an experiment that is about as clean and direct as physics ever gets. They wanted to know whether light changes frequency as it moves through a gravitational field, whether light loses energy climbing up and gains energy falling down. So they took gamma rays, which are just very high-frequency light, and they shone them up a tower 22.5 meters tall inside a building on the Harvard campus, and they measured whether the frequency of the light arriving at the top differed from the frequency that had left the bottom. It did. The shift was tiny, a few parts in 10 to the 15th, which is a decimal point followed by 14 zeros and then a 1. But it was there, and it matched exactly what general relativity predicted, and the prediction had been sitting on the shelf for 52 years. Einstein made it in 1907, using nothing more than the principle that being accelerated and being in a gravitational field are equivalent situations. He wrote down what that would do to light. Then 52 years passed, and two men in Cambridge, Massachusetts, shone a beam up a stairwell and found the number waiting for them exactly where he said it would be. What gets me about this is not the confirmation. Relativity gets confirmed constantly. That is not news. What gets me is the gap. 52 years between the prediction and the measurement arrived precisely on target. But read the result the other way round, and it says something simpler and considerably stranger. Time runs slower at the bottom of a tower than at the top, not as a figure of speech, not as an approximation that becomes true in extreme conditions. In an ordinary building, in an ordinary decade, in a stairwell that hundreds of students walked up and down without giving it a thought, two physicists measured the fact that the rate of time depends on where you are standing. The strangeness was never out at the edge of the universe. It was in a building in Massachusetts in 1959, and we just did not fully see it yet. 12 years later, someone decided to take the same question and put it on an airplane. In 1971, Joseph Haffel and Richard Keating loaded cesium atomic clocks onto commercial passenger flights. Not specialized research aircraft. Not a military testbed with a scientific payload. Regular scheduled airline flights, with the clocks strapped into passenger seats like unusually expensive luggage. They flew them around the world in both directions, eastward and westward, and then they brought them home and compared them against identical clocks that had stayed on the ground the whole time. The clocks that flew came back different. Not broken, not malfunctioning. There was nothing wrong with them. They had simply measured a slightly different amount of time than the ones that stayed still. The airborne clocks differed from the ground clocks by roughly 59 nanoseconds, and that number matched almost exactly what the combination of special and general relativity predicts. Velocity slows a clock down, altitude speeds it up, and the two effects partly cancel each other depending on which way around the planet you fly. Almost exactly. There were small residual discrepancies which the experimenters noted carefully in their write-up, and which have remained quietly interesting to a handful of physicists ever since. But the headline result was clear, and it has never been overturned. Time is not the same everywhere. Move through space, accelerate, change your position in a gravitational field, and you will move through time at a different rate than someone who stayed put. Two objects, same starting point, same ending point, different amounts of elapsed time. Now, if you are the kind of person who finds that straightforward, yes, relativity, we know this next. I want to ask you something, and I want you to actually answer it rather than let it slide past. Do you feel the weight of what that means? Because what it means is that there is no single universal clock ticking in the background of reality. There is no master time that everyone shares. There is no cosmic metronome that the universe keeps step with. No moment that is happening everywhere at once. There are only local clocks, local rates, local durations. The universe does not have one timeline. It has as many timelines as it has objects moving through it. That was 1971, and it was a laboratory result in the sense that it took specialized equipment and a research grant and a paper in a journal. It was still, for most people, a curiosity, a fact about physics rather than a fact about their life. That changed completely, and it changed in the most ordinary way imaginable. Your phone knows where you are right now. It knows because of a constellation of satellites orbiting at roughly 20,000 kilometers of altitude, each one carrying an atomic clock. And those clocks, because the satellites are moving fast and because they are sitting higher up in Earth's gravitational field, run faster than clocks on the ground by about 38 microseconds per day. 38 microseconds sounds like nothing. It is far less than a blink. It is well below anything your nervous system could register, even in principle. If someone offered you 38 microseconds, you would not know what to do with them. But the global positioning system works by calculating your position from tiny differences in the arrival times of signals coming from several satellites at once. The arithmetic is exquisitely sensitive to timing, because light covers about 30 centimeters in a nanosecond, and a nanosecond is 1,000th of a microsecond. Small timing errors become large distance errors very quickly. If the engineers had not corrected for that 38 microsecond daily drift, if they had simply ignored the fact that time runs at a different rate up there than it does down here, the position errors would accumulate at roughly 11 kilometers per day your navigation would be useless within hours, not slightly off, useless. So every single positioning device on Earth, every time you ask your phone to take you somewhere, is silently applying a correction derived from the fact that time is not uniform. I find something quietly wonderful about that. The engineers who built the system did not sit down and debate the philosophy of time first. They did not convene a panel on whether temporal flow is fundamental or emergent. They did the calculation, applied the correction, and the thing worked. It has been working ever since. Every day, for decades, hundreds of millions of people have relied on a machine that only functions because it accounts for the fact that time is different in different places. Which means the strangeness we are discussing is not a theoretical curiosity waiting for some future experiment to make it real. It is already baked into the infrastructure of modern life. It is in your car, it is in your pocket, it has been there the entire time. So the question was never whether time behaves this way. We know it does. We rely on it. We have built a civilization on top of it. The deeper question, the one that keeps showing up in experiment after experiment, and the one this whole video is chasing, is whether the thing we are measuring when we measure time is actually time, or whether it is something else, something we have been calling time because we never had a better word for it. And in 2021, that question came a great deal closer to home, because up to this point, every effect we have talked about has required a satellite, or an airplane, or a tower, something with a real separation you could point at. The next experiment needed 1 millimetre. Part 4, 1 millimetre and the end of the shared now. Something that should have been impossible happened in 2021, and the fact that most people never heard about it says something about how poorly we communicate the genuinely strange results in physics. A team at Gila in Boulder, Colorado, the same city, a few minutes down the road from the clock we opened with, measured the difference in the flow of time between two layers of atoms separated by 1 millimetre. Not 1 kilometre, not 1 metre, 1 millimetre, roughly the thickness of a credit card. And the difference was real. It was measurable. The atoms at the top of the sample experienced time passing at a fractionally faster rate than the atoms at the bottom, exactly as general relativity predicts for objects sitting at different heights in a gravitational field. The precision required to detect this was 7.6 times 10 to the power of minus 21, a decimal point followed by 20 zeros before you get to a meaningful digit. Now let me say what that means in the way that actually lands, rather than the way that keeps it safely at arm's length. Right now, as you are listening to this, time is passing slightly faster at the top of your head than at your feet. Your head is aging at a different rate than your shoes. I want to spend a moment here, because this is the most intimate result in this entire video and it deserves more than a sentence. Notice where you are, wherever you have settled, a bed, a chair, the floor, a train seat. Notice the distance between the crown of your head and the soles of your feet. It is not a large distance. It is a distance you cross 100 times a day without thinking about it, the length of your own body, the most familiar measurement there is. Now travel down it slowly. At the top, where your hair is, space-time is very slightly less curved by the mass of the planet beneath you. Down at your feet, a metre or so closer to the centre of the Earth, it is very slightly more curved. And because the rate of time depends on that curvature, as Pound and Rebka measured in a stairwell and as Gila measured across a millimetre, time is running fractionally faster up at the crown of your head than it is down at your feet. Your body is not aging as one single thing. It is aging as a gradient. This has been true every second of your life, in every bed you have ever slept in. Every time you stood up, every time you lay down, the top of you and the bottom of you were keeping slightly different time, and neither of them was wrong, and there was never a moment when they agreed. And then the gentleness of it, which I think is important. The difference over an entire human lifetime is far too small for anyone to ever notice. It is not going to change anything about you. Your head will not outlive your feet in any way that matters, but it is not zero. It is a real, physical, measured fact about your body, and it is happening right now while you lie there. Here is where it gets uncomfortable in a way the satellite example never quite manages. The GPS case tells us that time runs differently at different altitudes, and we accept it easily, because the altitudes are enormous and the satellites are far away and the whole thing feels appropriately cosmic. Fine. Space is strange. Space has always been strange. The Gila result pushes into territory that feels different. If time is that sensitive, that local, that dependent on your exact position in space, Then what exactly is the thing we are measuring when we say the word time? Is there one thing called time, or is there just a collection of local rates that we bundle together under a single word for convenience? And if it is the latter, if time is a useful fiction we construct out of our immediate surroundings, then what does it mean to say that the universe has a history? What does it mean to say that something happened before something else? I find myself with no clean answer to that, and every experiment that follows makes the question sharper rather than easier. Now, you might reasonably think that a millimetre's worth of difference is a laboratory curiosity, real, but so small it can never touch an actual life. It has already touched actual lives, and it has been measured on people by name. The twin paradox is the most famous thought experiment in relativity. One twin travels at high speed, comes home, and finds they have aged less than the sibling who stayed. It is in every popular physics book. It is used as a teaching device. It is not a thought experiment. It has been measured. Astronauts who spend 6 months aboard the International Space Station return to Earth having aged very slightly less than the people who stayed on the ground, on the order of 1/100th of a second. Scott Kelly, who spent close to a full year on the station, came home measurably younger than his identical twin brother Mark, who had stayed behind. The difference works out to roughly 5 milliseconds over 340 days. 5 milliseconds. It is nothing. It is less than the time it takes a hummingbird to beat its wings once. Nobody's health changed. Nobody's face looked different. And it is completely real. And it is the most concrete demonstration I know of something that ought to be much more famous than it is. 2 people, born at the same moment, who started out with identical biological clocks, lived through different amounts of duration during the same stretch of history. They experienced different quantities of time. The part of this that gets overlooked in the standard telling is not the 5 milliseconds. It is what the 5 milliseconds imply about the concept of a shared present. When Scott Kelly came home, he and his brother were standing in the same room, same place, same conversation. But the amount of time each of them had passed through since they were born was different. Their nows were not the same now. And if that is true for 2 men separated by 400 kilometers of altitude and a bit of orbital velocity, it is true in principle for any 2 objects anywhere in the universe. Einstein worked out the full version of this in 1905, and it is worth taking seriously rather than filing away as too abstract a matter. He showed that 2 events which are simultaneous for one observer are not simultaneous for an observer moving relative to the first. This is not an illusion produced by signal delays or imperfect instruments. It is not a limitation of our measuring devices. It is a genuine feature of the geometry of space-time. The events really do occur at the same time in one frame of reference and at different times in another, and neither frame is more correct than the other. Both are equally valid descriptions of reality, which means the concept of now, a single present moment stretching across space, a slice of the universe that is happening simultaneously everywhere, is not a feature of the universe at all. It is a feature of a particular point of view. Change your velocity, and your now changes with you. Events that were in your future become simultaneous with your present, or slip into the past for someone moving differently. Some philosophers and physicists have taken this to imply that all moments of time exist equally. Past, present, and future all equally real, with the sense of flow being a trick of perspective. Others, including the philosopher of physics David Albert, have pushed back hard, arguing that this interpretation smuggles in assumptions about what real means that the physics does not actually force on us. That argument is still live, and I am not going to try to settle it here. What is not in dispute is the underlying physical fact. The present moment as you experience it is a local phenomenon. It is real for you, and real for everything in your immediate vicinity, and it is not a global fact about the state of the universe. There is no universal now, and once you accept that, not as an abstract result on a page, but as a physical statement about the structure of reality, the question that follows is one I do not think has a comfortable answer. If there is no shared present, what exactly is the universe doing right now? We have established that the rate of time is local. That is settled physics. But there is a second property of time, one that feels even more basic than its rate, and it turns out to be in much worse shape. The direction. Part 5. The arrow that is not in the equations. Here is something that physics has known for about 130 years and has never quite figured out what to do with. Take any equation that describes how the physical world behaves. Newton's laws of motion, Maxwell's equations for electricity and magnetism, the Schrödinger equation of quantum mechanics, the field equations of general relativity. Take any of them. All of them. The full working toolkit of physics, everything we use to predict what matter and energy will do. Run them forward in time, now run them backward. The mathematics works identically in both directions, not approximately, not with small correction terms that you can neglect, identically. Which means that nothing in the fundamental laws of physics requires time to move in the direction you experience it moving. The universe, as far as its own equations are concerned, has no preference. Forward and backward are the same to them. Think about how strange that is against the texture of your actual life. You remember yesterday and not tomorrow. Coffee cools. It never spontaneously heats up. Eggs break and do not reassemble. People age in one direction. Every single thing you have ever observed happens in an order, and that order never runs the other way. And the laws governing every particle involved in all of that do not contain the direction at all. Ludwig Boltzmann ran head first into this in the 1870s and 1890s, and by most accounts it nearly broke him. He spent years trying to explain why we perceive a direction, past to future, cause before effect, when the underlying rules are perfectly symmetric. He was arguing about it in public, defending his work against colleagues who thought the whole project was misguided, and the personal cost of that fight was considerable. What he eventually concluded is the answer we still use today, and I want to be honest about how thin it is. The arrow of time is not a law. It is a statistical bias. Here is the reasoning. The universe started in an extremely ordered state. Very low entropy, everything arranged in a highly specific configuration. From that starting point, disorder increases, not because any law demands it, not because there is a force pushing toward messiness, simply because there are overwhelmingly more disordered arrangements than ordered ones, and random processes drift toward whatever is more probable. Picture a deck of cards fresh out of the box, sorted by suit and rank. Shuffle it. It becomes disordered, and it stays disordered, and no amount of further shuffling will sort it again. Not because shuffling is a one-way operation, every shuffle is perfectly reversible, but because there is exactly one sorted arrangement and something like 80 unvigintillion unsorted ones. The odds are simply overwhelming. That is the entire explanation for why time has a direction, not a fundamental law, a tendency produced by the arithmetic of large numbers, and it raises a question that Boltzmann never answered, and that nobody has answered since. Why did the universe start in such an ordered state in the first place? That initial condition, that improbably tidy beginning, is doing all the work, every bit of it. Remove it and the arrow of time disappears entirely. Past and future become indistinguishable. Memory stops meaning anything. Cause and effect collapse into each other. The whole structure of before and after, which is the frame you have hung your entire existence on, rests on one fact about the opening moment of the universe that no theory predicts and nobody can explain. To me, that is one of the most unsettling facts in all of science, and I want to slow down and put it plainly, because it is easy to nod along without letting it land. Everything you experience as the passage of time is downstream of an unexplained coincidence. Your memory of this morning, the fact that you can remember it at all and cannot remember tomorrow, the sense that the past is fixed and finished and the future is open and undecided, the feeling of being carried somewhere, the aging of your body, the order of the events in your life, the fact that they happened in a sequence and that the sequence means something, all of it, not grounded in a law of nature, grounded in the fact that the universe happened to begin unusually tidy, for reasons no theory supplies, before there was anything in existence capable of noticing. Nobody chose that. Nothing required it. And every framework we are going to look at tonight either assumes it or tries to explain it and fails in an instructive way. Now, if the arrow of time comes from statistics rather than from the laws themselves, you might reasonably expect something specific. You would expect that at small scales, down at the quantum level, where individual particles live and where statistics have not yet had a chance to take hold, time would already start to look symmetric. The arrow should thin out and vanish as you zoom in, the way a photograph dissolves into grain. That expectation turned out to be correct, and it turned out to be correct in a way that is considerably harder to dismiss than most people realize. Andrea Rocco and Thomas Guff at the University of Surrey were looking at what physicists call open quantum systems. That phrase sounds technical, but the meaning is simple. Quantum systems that interact with their environment, which is basically everything real, since nothing in nature is perfectly isolated. A perfectly sealed quantum system is a textbook idealization. Actual quantum systems leak. They exchange energy and information with whatever surrounds them, constantly. And that leaking is where the arrow of time was supposed to live. The standard story says irreversibility comes from information dissipating outward into the environment, never to be recovered. Energy spreads. Correlations disperse into the surroundings. You cannot gather them back. That, supposedly, is where forwardness comes from. Rocco and Guff wanted to understand exactly how that works, why time appears to flow forward in these systems even though the underlying equations are symmetric. What they found, published in February of 2025, is that it does not work. Even after applying the standard simplifying assumptions that everyone in the field uses, even after fully accounting for the way energy and information dissipate into the environment, the equation still behaved the same way whether time moved forward or backward. The mathematical object sitting at the heart of the description, what they called the memory kernel, turned out to be symmetric in time. The arrow was not emerging from the physics of the system. It was simply not there. Guff described his reaction as surprise. That is a careful word for a physicist to use in public, and it is worth noticing, because what it means is that the result went somewhere the mathematics was not expected to go. So where does that leave us? It leaves us with the direction of time that is not in the fundamental laws, and that does not emerge from the quantum processes underneath our reality either, which means it is being generated by something sitting above the level of the equations. And the obvious candidate, the thing that keeps showing up in result after result, in a way that becomes almost impossible to ignore once you start noticing it, is the observer, the thing doing the looking, which raises a question that feels almost too strange to ask seriously. What if the direction of time is not a feature of the universe? What if it is a feature of what it means to be aware of the universe? What if it is us? That question is not metaphysics. That is the thing I want you to hold on to. It sounds like metaphysics, and for most of the 20th century it would have been treated as metaphysics, and a physicist who spent time on it would have been quietly steered toward more productive work. It has a physical answer. It has an experimental answer. And getting to it requires something a man at IBM proved in 1961, about a subject that seems at first to have nothing whatever to do with time. Part 6. Information is physical. Rolf Landauer was working at IBM in 1961, and he asked a question that sounds like it belongs to engineering rather than to fundamental physics. Does processing information cost energy as a matter of physical law, or does it only cost energy because our machines happen to be clumsy? At the time, this was a live practical concern. Computers ran hot. They still do. Anyone who has held a laptop on their lap for an hour knows that thinking, in a machine, produces heat. The assumption was that this was an engineering failure, that with better design, better materials, better circuits, you could push the heat down toward nothing. Waste heat was a defect, not a requirement. Landauer proved otherwise, and his answer connected the digital world to the deepest law in physics. He showed that erasing one bit of information, forcing a 1 into a 0, wiping out which state a switch used to be in, clearing a single memory register, necessarily releases a tiny amount of heat into the environment. Not because of inefficiency, not because we are bad at building things, because the second law of thermodynamics requires it. The reasoning is beautiful, and once you see it, you cannot unsee it. When you erase a bit, you take a system that could have been in either of two states, and you force it into one known state. You have reduced the number of possible arrangements, you have destroyed a possibility, and the second law does not permit that lost possibility, that lost entropy, to simply vanish from the universe. It has to be paid for. It gets exported into the surroundings as an unavoidable minimum puff of heat. Landauer calculated the size of that minimum. At room temperature it comes out to roughly 3 × 10 to the minus 21st joules per bit, a quantity so small it is almost comic, about 1/50th of an electron volt. But it is a flaw. No amount of clever engineering will ever get below it, in any machine, made of anything, anywhere in the universe. Two things follow, and both matter for tonight. The first is the headline. Information is physical. A bit is not an abstract nothing that floats free of the material world. It is a real thing with a real thermodynamic cost. The contents of a memory are as physical as the mass of a stone. The second is the detail that most summaries skip, and it is the one that matters here. The minimum cost scales directly with the temperature of the environment. Hotter surroundings, more expensive the erasure, which means, quite literally, that thinking is more expensive in a hot room than in a cold one. Memory is not free, and its price varies with the weather. For 50 years this was treated as elegant theory with no practical bite, because real computers dissipated billions of times more heat per bit than Landauer's flaw. The limit was so far below anything achievable that it was effectively decorative. Then, in 2012, a team finally measured it directly, trapping a single microscopic particle in a double well and showing that erasing its one bit of information dissipated heat that saturated exactly at the predicted bound. The flaw is real, and we have now stood on it. And this connects to time in a way that took decades for anyone to fully appreciate. Follow the chain slowly, because each link is solid and the conclusion is not obvious. The arrow of time is related to entropy. That is Boltzmann's answer from the last part. The direction of time comes from disorder increasing, and entropy is the measure of that disorder. Every act of observation increases entropy. That is Landauer's result. Recording information, building a memory, writing something down in any physical medium, all of it necessarily produces entropy somewhere. Therefore, observation is not a passive window onto reality. Observation is a thermodynamic event. It produces heat, it generates irreversibility, it creates entropy. And entropy is the only thing in all of physics that distinguishes the past from the future. That is not a rhetorical flourish, it is the actual situation. Strip away entropy, and every fundamental equation becomes indifferent to direction. Entropy is the whole difference. So observation does not merely register the arrow of time, observation participates in producing it. What I find remarkable about this, and I want to say it in the smallest possible terms because the small version is more unsettling than the grand one, is that it means every time you remember something, every time you store information about the past, you're not just recording time. In the most literal thermodynamic sense, you are generating it. Your memory is an engine running against the second law of thermodynamics, and the exhaust from that engine is, in some real sense, the difference between yesterday and tomorrow. There is a physical price for having a past, and it is paid in heat, every single time by whatever is doing the remembering. Which raises a question that deserves considerably more attention than it usually gets, and which is the exact hinge this video turns on. If memory creates the arrow of time, and the arrow of time is what makes the past different from the future, then what came first? Did time produce memory, or did memory produce time? That is not a question you can answer by thinking about it harder. It is a question you answer by building something and measuring it. In November of 2025, a team at Oxford did exactly that. They built the smallest clock anyone has ever built, and then they did something nobody had thought to do with a clock before. They measured what it cost to look at it. Part 7. The clock. That cost 1 billion times more to read than to run. The result that Natalia Aries and her colleagues at Oxford published in November of 2025 is one of those things that takes a moment to fully land, and I think most people who encounter it move past it too quickly. So we are going to move through it slowly. They built a microscopic clock. Physically, it is a double quantum dot. 2 tiny regions fabricated on a chip close enough together that a single electron can jump from one to the other. That is the whole device. Each jump is a tick. The clock works. It keeps time in the most minimal sense that anything can be said to keep time. There is a repeating event, and you can count the repetitions, and counting them tells you how much time has gone by. This is a clock stripped down to nothing. No pendulum, no crystal, no atom, no laser. 1 electron and 2 places for it to be. Then they asked a question that sounds almost too basic to be worth asking. How much energy does it cost to run this clock compared to how much it costs to read it, to observe it, to detect the ticks, to turn quantum events into a record that persists? Nobody had really separated those two things before. When you look at a wall clock, the running and the reading feel like the same activity. The clock ticks whether or not you glance at it, and glancing at it costs you nothing worth mentioning. Light was going to bounce off the clock face anyway. The answer was not what anyone expected. Reading the clock required up to 1 billion times more energy than running it. Not twice as much, not 10 times as much, not 100 times, 1 billion. I want to leave that number alone for a second, because it is doing more work than any interpretation I could layer on top of it, 1 billion. The clock itself, the actual physical process of an electron moving back and forth between two dots, which is to say the actual passage of time in this system, is almost free. It costs essentially nothing. The universe runs that process without breaking a sweat. Watching it costs 1 billion times more. And when they analysed where all that energy was going, they found it was producing entropy. The act of measurement was generating irreversibility. It was creating, in that tiny apparatus, precisely the thermodynamic conditions that make one direction of time distinguishable from the other. But the detail that matters most in this experiment is not the ratio. It is what happened when they turned the asymmetry off. When the two quantum dots reached the same temperature, when the system was perfectly balanced, with no thermal gradient pushing anything in any particular direction, the electron jumped forward and backward with equal probability. The clock had no direction. It was equally past and future. There was still motion. There were still jumps. Things were still happening. But there was no sequence to them in any meaningful sense, no way to say that this state came before that one. Time, in that state, had no arrow. The arrow appeared only when the measurement apparatus recorded the jumps, only when something outside the quantum system built a memory of what had happened. The direction of time in this experiment was not a property of the clock. It was a property of the act of looking at the clock. So here is the question I cannot get out of my head after sitting with this result, and I am going to pose it now and then leave it hanging, because we are not equipped to answer it yet. If you removed every observer from the universe, every device, every memory, every record of any event, everything that retains information about a previous state, would time still have a direction? The experiment does not answer that. It cannot. But it makes it very difficult to say yes with any confidence. Let me slow down further, because the mechanism inside the Oxford experiment is where the strangeness really lives, and it is worth looking at carefully rather than accepting the summary. The electron sits between two quantum dots. It can jump left or right. At the quantum level, with no measurement happening, these jumps are symmetric. The electron has no preference. Left and right are equivalent to it. Forward and backward are indistinguishable. There is no tick. There is just motion, a kind of formless back and forth with no more structure than the shimmer of heat above a road. Now the measurement apparatus turns on. It records each jump. It builds a sequence. Left, right, left, left, right. And that sequence has a direction. It has a before and an after. It has a past and a future. It has an order that cannot be rearranged without changing what the record says. The arrow of time appears the moment the record exists. And here is the part that should give you pause, because it rules out the easy explanation before you can reach for it. The arrow is in the record, not in the electron. The electron does not know it is being observed. It does not change its behavior because of the measurement. Nothing about the physics of that electron is different from what it would have been if the apparatus had stayed off. This is not the electron responding to being watched. This is not some spooky influence reaching down and altering the particle. The entropy, the irreversibility, the thing that makes past different from future, is generated entirely in the measurement apparatus, in the act of writing the result down, in the physical business of creating and maintaining a record. Which means, if you follow it through, that you can imagine a universe with no records, no memories, no structures that retain information about previous states, nothing anywhere that keeps track. That universe would have electrons jumping back and forth, energy moving around, fields fluctuating, things happening in the sense that states would be different from one another, but no arrow of time, no past, no future, just an eternal symmetric present. That is not science fiction. That is what the Oxford experiment implies, and the people who ran it are careful, sober experimentalists who would not thank me for overselling their work. So let me put the honest boundary on it. What they measured is a thermodynamic fact about a specific apparatus. Reading costs vastly more than running, and the cost appears as entropy. What that means for the universe as a whole is interpretation. Serious people disagree about it. I am going to give you the disagreement in full before the end of the night, but the interpretation connects directly to something John Wheeler argued for decades, and it is worth introducing him now because he is going to come back at the very end. Wheeler's position was that information is not a description of physical reality, that at its deepest level, the universe is not made of matter and energy at all, but of bits, records, questions answered, distinctions drawn. If that is right, then time itself is a record a memory the universe keeps of itself. And the question of what is doing the remembering does not have a clean answer yet. We have now established something remarkable, and I want to make sure it is fixed in place before we go on, because the next part is going to move the ground again. The rate of time is local, that is Pound and Rebka, Haffel and Keating, Giller and the twins. And the direction of time is not in the laws, is not in the quantum layer, and appears wherever a record is kept. That is Boltzmann, Surrey, Landauer and Oxford, which leaves one more property of time that we have not questioned yet. Something so basic that it feels beneath questioning. The order, not how fast, not which way. Just, does one thing happen before another thing, or does it not? Part 8. The time that quantum mechanics forgot. If the arrow of time lives in the record rather than in the physics, the next question arrives almost on its own. What does quantum mechanics actually say about time to begin with? And the answer is stranger than most people realize, because quantum mechanics barely says anything about time at all. In every other part of physics, time and space are treated as partners. General relativity weaves them together into space-time, a single fabric that bends and stretches and curves in response to mass. They are not two separate things that happen to coexist. They are aspects of one geometric object. That is the whole insight. In quantum mechanics, that partnership does not exist. Space is unobservable. You can measure position, you can ask a quantum system where it is, and the question is well formed, and the system has an answer, and position enters the mathematics as a property the system itself possesses. Time is not an observable. Time is a parameter. It is a number you feed into the equation from outside, like setting a dial before you run the experiment. The Schrödinger equation treats time as something that simply flows in the background, uniform and external, entirely untouched by anything the quantum system does or is, which is almost exactly what Newton said in 1687. Absolute time, flowing equably, independent of anything external. Quantum mechanics, the most revolutionary framework in the history of physics, the theory that overturned determinism and locality, and the very idea of an object having definite properties, quietly smuggled Newton's absolute time back in through the side door and never quite admitted it. John von Neumann formalized this in 1932, and the formal statement is stark. Time in quantum mechanics is not an operator, it is a given. Sit with the consequence of that for a moment. Every quantum experiment ever run, every result we have, every prediction we have ever tested, in a century of the most successful physics anyone has ever done, all of it was conducted inside a framework where time was assumed rather than derived. We have never measured time from inside a quantum system. We have only ever measured quantum systems from inside time. Whether those two things are the same turns out to matter enormously, and in 2020 a team in Vienna, including the physicist Giulia Rubino, decided to stop treating it as a theoretical problem and actually push on it in a laboratory. What they were testing sounds like it belongs in a philosophy seminar rather than a physics lab. They wanted to know whether the sequence of events in a quantum system has to be fixed. In classical physics, causality is absolute. If A causes B, then A precedes B. The order of events is not a matter of opinion or a matter of measurement. It is written into the structure of reality. Cause first, effect after. That is not a rule anyone imposed. It seems to be the shape of the world. They set up a situation where a quantum particle passes through two operations, call them A and B, and the order in which it experiences them is placed in quantum superposition. Not randomly one or the other, which would be uninteresting. That is just ignorance, and you could resolve it by looking. Both, simultaneously. A before B and B before A, at the same time, in the same experiment, for the same particle. And this was not a theoretical result, it was measured. The experiment produced outcomes that can only be explained if causal order is genuinely indefinite. Not unknown, not random, superposed. So here is what that actually means, and I want to state it in the flattest language I can find, because the flat version is the one that is hardest to slide past. Causality, the principle that causes precede effects, that the past shapes the future and not the other way around, is not a fundamental feature of quantum reality. It is something that emerges at larger scales, the way temperature emerges from the motion of molecules, the way solidity emerges from mostly empty atoms. Underneath, at the quantum level, before and after are not fixed. The universe does not have a built-in before. It has a before only, when something forces the order to become definite. Which, if you have been following the thread from Boltzmann through Landauer through the Oxford experiment, is going to sound familiar. Let me step back here, because we are roughly halfway through, and there is a lot of ground behind us. Let me put the pieces on the table together and look at them. We started with a clock so precise it can check whether the constants of nature are drifting. We found that the rate of time is local, that clocks disagree depending on where they are and how fast they are moving, that this has been measured on towers and airplanes and satellites and across a single millimetre, and that it has been measured on a pair of twin brothers. We found that there is no shared present moment anywhere in the universe, not between you and anyone else, not ever. We found that the direction of time is absent from the fundamental equations, which run identically in both directions, and that Boltzmann's statistical explanation for the direction we experience rests entirely on one unexplained fact about the beginning of everything. We found that the direction is not hiding in the quantum layer either. Surrey went looking and the mathematics came back symmetric. We found that the direction shows up in the record, that reading a clock cost 1 billion times more than running it, that the cost appears as entropy, and that entropy is the only thing in physics that separates past from future. And now we find that causal order itself, the sheer question of whether one thing happened before another, is not built in. It also has to be fixed from outside. Every single property of time we have examined has turned out to be something that needs a viewpoint, a position, a record, a measurement. Not one of them has turned out to be a feature the universe possesses on its own, that something keeps pointing back toward the same place, toward the observer, toward the record, toward whatever is doing the measuring. Whether that is a satisfying answer, or whether it is the beginning of a much deeper problem, is something I genuinely do not know, and I want to be honest that the people who have spent their lives on this do not agree about it either. But there is one more thing to look at before we get to their disagreement, and it is the largest single result in this entire video. Because in 1967, 2 physicists sat down and tried to do the most obvious thing anyone could do with the tools available. They tried to write down the equation for the whole universe, and when they did, time vanished from it. Part 9. The equation with no time in it. John Wheeler and Bryce DeWitt were not trying to do something exotic. I want to establish that first, because the result sounds like it must have come from someone deliberately chasing paradox, and it did not. They were trying to do the obvious thing, write down the quantum mechanics of the universe as a whole, not the quantum mechanics of a particle, not of an atom, or a molecule, or a laboratory apparatus. The universe, all of it, one equation. This is a reasonable thing to want. Quantum mechanics is supposed to be universal. It applies to everything, and the fact that we normally use it on small things is a practical matter, not a limitation of principle, and general relativity applies to everything too at the large scale. So if both theories are true, there ought to be a single description that covers the whole thing at once. When you attempt this, you immediately run into a technical problem. General relativity describes how the geometry of space-time evolves over time. Quantum mechanics describes how quantum states evolve over time. To combine them, you need a single equation that handles both, one that treats the geometry and the quantum state together as a single evolving thing. So they wrote it. And when they finished, in 1967, time was gone. Not approximately gone. Not gone in some particular limiting case that you could work around. The time variable, the letter t that appears in essentially every other equation in physics, the thing that everything else is a function of, was simply absent from the final result. There was no place to put it. It did not survive the derivation. The equation describes the universe completely, and it contains no time, which means the universe as a whole, described by the most complete equation physicists have been able to construct, does not evolve in time. It just is, static, timeless, a single quantum state, with no before and no after, no earlier and no later, not a process, not a history, a thing. This is called the Wheeler-DeWitt equation, and I want to be very clear that it is not a fringe result that got quietly buried. Quite the opposite. It is the starting point for essentially every serious attempt at quantum gravity that has been made in the last 57 years. Anyone working on unifying quantum mechanics with general relativity has to reckon with it. It is foundational, and what it says, with complete mathematical clarity, is that time is not a fundamental feature of the universe. It is something that has to emerge, somehow, from a timeless underlying reality. The question is how? How do you get time out of a universe whose own equation contains none? There are several candidate answers, and I want to be honest that none of them are fully satisfying. But in 2013, one team decided to stop debating the candidates and actually test one of them in a laboratory. What they found is one of the most quietly unsettling results in modern physics, and it almost never comes up outside specialist conversations. The idea they were testing had been proposed 30 years earlier, in 1983, by Don Page and William Wouters. It is called the relational interpretation of time, and the logic runs like this. If the universe as a whole has no time, as the Wheeler-DeWitt equation says, then time must arise from the relationship between parts of the universe, specifically between a clock and an observer of that clock, not from either one alone, from the correlation between them. Ekaterina Mareva and her colleagues built the simplest possible physical version of that idea. Two entangled photons, one acted as the clock, the other acted as the observer. Then they looked at the system in two different ways, and this is where it becomes remarkable. First, from the outside, they treated the whole two-photon system as a single object and measured it from without, the way you would measure any sealed system you were standing outside of. From that perspective, the system appeared static, timeless, no evolution, no change, no before or after, exactly what the Wheeler-DeWitt equation predicts for a universe described as a whole. Then they looked from the inside. They used one photon to measure the other, letting the internal observer track the internal clock, exactly as Page and Wouters had described. From that perspective, time existed. The clock ticked. Events had a sequence. The internal observer experienced time passing. Same system, same physical setup, same photons, same apparatus, same afternoon. Two completely different realities depending on where you stood. If you were outside, the universe had no time. If you were inside, it did. Part 10. Inside and outside. I want to put you in both positions because reading the Mareva result is one thing and standing in it is another. Imagine you're outside. There is a sealed system in front of you. Inside it, two entangled photons. You're not part of it. You're separate from it, looking at the whole thing at once, and your job is to describe it as a single object. From here, nothing happens. There is no ticking. There is no earlier and no later. There is no moment at which the system is doing one thing and a subsequent moment at which it is doing another. The system simply exists, complete, all at once, the way a written sentence exists on a page rather than unfolding over time. Every part of it is there simultaneously if the word simultaneously even applies, which it may not. It is not empty. There is structure in there, relationships, correlations, a great deal of information, but there is no flow. Nothing is going anywhere. Nothing is becoming anything. I do not think this is a frightening picture. I want to say that, because it can be described in a way that sounds bleak, and I do not think bleak is the right register. It is more like a profound quietness, a thing that is finished and always was. Now move inside. You're one of the photons. You're not looking at the system anymore. You are in it, and you are looking at the other photon. And suddenly there is a tick, then another. Something happened, and then something else happened after it. And the difference between those two events, the fact that one came first, is the entire content of what we mean by time. Now it is flowing. Now there is a before, and you are past it, and there is an after, and it has not arrived yet. You have a history. You're in the middle of something, and here is the part that matters most. Nothing about the system changed, not one thing. The photons are the same photons. The apparatus is the same apparatus. The physical state is identical in both descriptions. The only thing that changed is where you are standing. Now the detail that makes this land, and it is the reason this experiment belongs at the center of this video rather than in a footnote. The universe, by definition, has no outside. There is no position anyone can occupy that is not inside it. That is not a technological limitation waiting for a better spacecraft. It is what the word universe means. Everything is in it, including you, including every instrument you could ever build, including any observer of any kind anywhere. Which means the timeless description, the Wheeler-DeWitt equation, the static quantum state, the universe with no before and no after, is a description from a perspective that physically cannot exist. No observer can ever stand there. The only description any real observer will ever have access to is the internal one. the one where time exists. And here is where I want to be extremely precise, because the loose version of this is wrong, and the loose version is what usually gets repeated. This does not mean time is an illusion. It means something more specific, and I think more interesting than that. It means time is real, but only locally, only from inside, only for participants. The universe does not have a single time that everyone shares. It has a collection of local times, each one arising from the relationship between a particular observer and a particular clock. What we call time, the thing we measure and feel and organize our entire existence around, the thing that structures every human life that has ever been lived, is something that emerges from entanglement, from quantum correlations between the parts of a system that has no global time at all. What I find genuinely vertiginous about this is not the conclusion. It is the question it opens at the boundary. If time emerges from the relationship between observer and system, if it is not a backdrop but a product, then what happens at the edges of that relationship? What happened to time before observers existed? Was there a then at all? And notice that the question eats itself, because the word before already assumes the thing we're trying to explain. You cannot ask what came before time without using time to ask it. Every attempt to reach behind the curtain has to use the curtain to get there. That is not a rhetorical trick. It is the actual shape of the problem, and we are going to run into it again at the end of the night in a form that is much harder to escape. Now I want to add one more piece, briefly, because it connects the smallest scale to the largest, and it bears directly on whether the past is even a definite thing. Stephen Hawking showed in the 1970s that black holes emit radiation. It is called Hawking radiation, and it arises from quantum effects near the event horizon, and it means black holes are not permanent. They slowly evaporate. The trouble is what that radiation carries. It is thermal, it has energy, but it carries no information about what fell into the black hole. It is, as far as anyone can tell, random. So as a black hole evaporates, the information about everything that ever fell into it, every particle, every quantum state, every bit of physical data, appears to be gone, not hidden, not encoded in correlations too subtle for us to detect. Gone. This violates unitarity, which is the requirement in quantum mechanics that quantum evolution is reversible and that information is always conserved. Unitarity is not a small technical rule. It is one of the structural commitments of the whole framework, and if information can be destroyed, then the past cannot be reconstructed from the present, even in principle. The chain of cause and effect that makes the past a well-defined thing becomes undefined for anything that has ever crossed an event horizon. The reason this belongs in a conversation about time is that temporal order and information preservation turn out to be the same thing viewed from different angles. To say that the past is definite, that events happened in a specific sequence, that there is a fact of the matter about what occurred, is to say that information about those events is preserved somewhere in the present. That is what makes it a fact rather than a story. If black holes destroy information, they destroy the definiteness of the past. They introduce a genuine ambiguity into the timeline of the universe that no experiment from outside can resolve, and there are a great many black holes. I'm not going to take this any further, because it is a live and heavily contested area, and it deserves a video of its own rather than a paragraph. Serious people have been arguing about it for 50 years, and some of them now think the information does survive after all, encoded in ways we're only beginning to understand. But it sharpens the question we're carrying. If the past is not fully definite, if the timeline of the universe has genuine gaps in it, then what exactly is the thing we're trying to measure when we point a clock at reality? And then, just when the picture seems as strange as it can get, someone reflects a wave backwards through time in a laboratory and demonstrates that the one-wayness of everything we have ever experienced was never a law in the first place. Part 11. Time has a mirror. Something physicists had been predicting since the 1960s, but had never managed to produce cleanly in a laboratory finally happened, and the result sounds like science fiction until you look at what it actually demonstrates. A team at the City University of New York, working in the group of Andrea Alou with Hoyong Musa as lead author, built a system that reflects electromagnetic waves in time rather than in space. Let me set up what that means, because the phrase does not immediately pass. Normally, when a wave hits a boundary, a wall, a surface, the transition between two materials, it reflects back through space. You have seen this every day of your life. Sound bounces off a canyon wall and comes back as an echoing repeat. Light bounces off a mirror and comes back toward you. The wave was travelling in one direction, it met a boundary in space, and it turned around in space. The cunning experiment created a temporal boundary instead. They did it by suddenly and uniformly changing the physical properties of the medium the wave was travelling through, shifting the electrical permittivity of the whole system essentially instantaneously, not changing it in one place, which would be an ordinary spatial boundary, changing it everywhere at once, at a single moment. They created a moment in time at which the wave experienced a discontinuity, and the wave reflected, not backward through space, backward through time. The signal began retracing its own history. It went back through the same medium it had already passed through, reproducing its own past states in reverse order. The team also observed something called frequency translation. The reflected wave emerged at a different frequency than the original, which is the temporal equivalent of a wave changing direction when it enters a different medium. The result was clean, it was repeatable, and it confirmed a theoretical prediction that had existed since the 1960s without ever being clearly demonstrated. Now, the mechanism is the part that reveals something about time that was always true and had simply never been shown this clearly, and I want to walk through it because it is genuinely elegant. When a wave hits a spatial boundary, a wall, what is conserved is its frequency. The pitch stays the same, the direction changes. That is why a sound bounced off a cliff comes back recognizably as the same sound rather than as a different one entirely. A temporal boundary works the opposite way. When the medium changes suddenly in time rather than in space, what is conserved is the direction. The wave keeps moving forward through space, but its frequency changes, shifting to a value determined by the properties of the new medium, and simultaneously a time-reversed copy of the wave is generated, propagating backward. Direction preserved, frequency changed. The exact mirror image of an ordinary reflection. And here is what makes this more than a clever piece of engineering. This is not a property of exotic quantum systems. It does not require anything unusual. It follows directly from Maxwell's equations, which are among the most tested relationships in all of physics, written down in the 1860s and used every day by every electrical engineer on the planet. Which means the capacity for time reversal is not something that has to be injected into physics from outside. It is already there. It has been sitting in the structure of the equations for 160 years, waiting for the right physical conditions. The Cunny team did not discover something new. They revealed something that was always present. And that is a different kind of result, and a more interesting one, because of what it says about the asymmetry of time. The fact that waves travel forward and not backward, that signals propagate into the future and not the past, that everything you have ever observed goes one way, that asymmetry is not written into the laws of electromagnetism at all. It is written into the initial conditions, into the fact that we start with a wave going in one direction, through a medium that stays uniform, change the medium suddenly, and the equations immediately produce both directions at once without being asked. I should give you the caution the experimenters themselves give, because it is scientifically correct and because I do not want to oversell this. Time outside the system continued perfectly normally. Nobody's watch ran backward. What changed was the behaviour of a wave inside an engineered temporal boundary. Nothing travelled to the past. But that caution, accurate as it is, does not fully dissolve the question the experiment raises. If the boundary between past and future is something that can be engineered, something that responds to the physical properties of a medium, something you can create on a bench with the right equipment, then what exactly is that boundary? What is it separating? And notice that Boltzmann has come back sharper than before. The arrow of time, even in classical physics, even in 19th century electromagnetism, with no quantum mechanics anywhere near it, is not a law. It is a choice of starting conditions. Which puts his unanswered question back on the table with considerably more force. Who chose the starting conditions? Or more precisely, was it a choice at all, or was it the only option available? That is not a rhetorical flourish. It is one of the genuinely open problems in physics, and we will come back to it. Now I have to complicate the picture, because there is a set of results from particle physics that points the other way, and honesty requires including them. In 2012, the Babar experiment at SLAC measured direct evidence of time reversal violation in subatomic particles. They were studying B mesons, unstable particles that can transform into their antiparticle equivalents. The question was simple. Is the process of going from state A to state B statistically identical to the process of going from state B back to state A? If time is truly symmetric, those rates should be equal. They were not. The transition rates differed by a measurable amount. Then in 2020, the T2K experiment in Japan found a related asymmetry in neutrinos, matter and antimatter versions of the same particle oscillating between different types at different rates. Both results are real, both are statistically robust, both have held up, and both show that the arrow of time is not merely a statistical tendency at large scales, the way Boltzmann described it. Something asymmetric is built into the behavior of individual particles. The standard model can accommodate this mathematically. It has a place to put it. What it cannot do is explain from first principles why the asymmetry is there. What bothers me about this is the gap between the explanations we have and the explanation we would actually need. Boltzmann gave us thermodynamics, the arrow of time as a statistical bias toward more probable states. That works at scale, and it explains why coffee cools and eggs do not reassemble. But Babar and T2K are showing something at the particle level that is not statistical at all. It is structural, built in at the level of individual interactions where large number statistics have no purchase. And a structural asymmetry demands a structural explanation. We do not have one, which means that the deepest source of time's direction remains unknown, even as our measurements of it become more precise every year. We can describe the asymmetry with enormous accuracy. We cannot say why it exists. And then there is one more result which points in almost the opposite direction from everything else in this part, and which I find the strangest of all of them. The Babar and T2K results show that time's direction is stamped into individual particle behavior. But there is a phenomenon in quantum mechanics that says observation can stop time entirely. It is called the quantum Zeno effect, first proposed by George Sudarshan and Baidyanath Misra in 1977, and confirmed experimentally many times since. The idea is this. A quantum system evolves over time. A particle decays, an atom transitions between energy levels. A quantum state changes into a different quantum state. That evolution has a characteristic timescale, a rate at which it happens. But if you measure the system frequently enough, if you observe it fast enough, the evolution slows down. The more often you look, the slower it changes, and in the limit of continuous observation, the system stops evolving entirely. It freezes. You can hold a quantum system in its current state indefinitely, simply by measuring it fast enough. The atom that was going to decay does not decay, not because you interfered with it physically, but because you kept checking. Now put that alongside the Oxford experiment. Observation creates the arrow of time. That is Oxford. The Zeno effect says observation also controls the rate of time, how fast quantum evolution proceeds. Frequent observation slows it. No observation removes the arrow entirely, and the act of observing costs energy, as Landauer showed 65 years ago, which means that controlling time at the quantum level has a thermodynamic price. You pay to slow it down, you pay to give it a direction. Time, in this picture, is not a river flowing along independently of everything around it, indifferent to whether anyone is there. It is something closer to a process that requires participation to sustain and participation to direct, which raises a question I find genuinely difficult to resolve, and which I will hand to you rather than pretend to answer. If observation sustains time, if the rate and the direction of time depend on the presence and frequency of measurement, then what was time doing before there was anything in the universe capable of observing anything? Was it doing anything at all? And if the answer is no, then what exactly started it? Part 12. The instruments running tonight. There is a detail about quantum transitions that does not fit comfortably into any of the frameworks we have been building, and I want to start this part with it because it changes what the word duration means. The event has a length, not a length measured by an external clock, a length written into the geometry of the material itself. Hugo Dill's team at EPFL showed this in February of 2026. They measured how long it takes an electron to absorb a photon and jump to a higher energy state, without using any external reference at all. That without is the whole result. Every previous measurement of this kind relied on a clock sitting outside the quantum system, timing it from without. You start a stopwatch, the event happens, you stop the stopwatch. The stopwatch is not part of the system. It is a separate thing, in the background, doing its steady external job, which means every previous measurement of a quantum duration was really a measurement of the quantum system against the flow of time, with the flow of time assumed. What Dill's team did instead was use the quantum system's own internal structure to record the duration. Here is how. When an electron absorbs a photon, it can follow multiple quantum pathways simultaneously. Those pathways interfere with each other, the way any waves interfere, and the interference leaves a signature in the spin of the emitted electron. By analysing that signature, the team could work out how long the transition took, entirely from information encoded inside the process itself. The clock was the event, there was nothing outside it, and what they found is that quantum transitions are not instantaneous. They have a measurable duration. But the duration depends on the atomic structure of the material. Change the symmetry of the crystal, and the transition takes longer. Lower symmetry, longer time. Higher symmetry, shorter time. The geometry of the material determines how long the quantum event lasts, not an external clock, not the flow of time in the background, the shape of the thing itself. This sits in the same family as the Wheeler-DeWitt result in the Mariva experiment, and it asks the same uncomfortable question from a new direction. If the duration of a quantum event is determined by internal geometry, rather than by external time, what exactly is flowing? When we say time flows, is it possible that what we are calling time is just a way of describing the internal geometry of processes? That duration is not something events happen inside, but a property that events carry, the way they carry mass or charge. I do not know how to make that idea comfortable, but I also do not know how to dismiss it. Now, I want to widen out, all the way out, because the same kind of crack has opened at the largest scale we can measure, and it has been sitting there refusing to close for about a decade. There is a number at the centre of cosmology called the Hubble constant. It is the rate at which the universe is expanding. It should be one number. There is one universe. But when physicists measure it two independent ways, they get two different answers. The first method uses the cosmic microwave background, the faint afterglow of the early universe, the oldest light there is, mapped with extraordinary precision by the Planck satellite and published in 2018. Run that through the standard cosmological model, and you get 67.4 kilometers per second per megaparsec. The second method uses Cepheid variable stars as distance markers, work led by Adam Rees and his team. Those stars pulse at a rate that reveals their true brightness, which lets you calculate how far away they are, which lets you measure the expansion directly. That method gives 73.2. The disagreement is roughly 5 sigma. 5 sigma is the threshold physicists use to declare that something is a discovery, rather than a fluctuation, a gap that large almost certainly cannot be explained by measurement error. Both teams have gone back over their work repeatedly, for years, looking for the mistake. The numbers do not converge, and here is why this belongs in a conversation about time rather than just about space. The Hubble constant is not merely a rate of expansion, it is a rate of change in the geometry of spacetime itself. It tells you how fast the fabric, including the time dimension, is evolving at cosmic scales. If two independent methods of measuring that rate disagree by 5 sigma, it means we do not fully understand how the geometry of spacetime is behaving on the larger scales, and if we do not understand that, then our entire picture of cosmic time, the 13.8 billion year timeline, the sequence of cosmic events, the ages of the oldest structures, is built on something that is not fully resolved. I find it hard to accept how casually this is sometimes described as a measurement problem rather than a physics problem. 5 sigma is not a rounding error, it is a signal, and in 2024, a second instrument made that signal considerably louder. The Dark Energy Spectroscopic Instrument spent years mapping the distribution of galaxies across enormous volumes of the universe, using the patterns in that distribution to measure how cosmic expansion has changed over time. What it found is that dark energy, the force driving the acceleration of the expansion, the thing Einstein originally called the cosmological constant, may not be constant at all. The data suggest it is weakening, slowly but measurably. It was stronger in the early universe and has been decreasing since. Dark energy is the engine driving the expansion of space, and the expansion of space is the mechanism by which the universe has a cosmic history at all. A sequence of events, an earlier and a later, a past and a future at the larger scales. If the engine is not constant, then the rate at which cosmic time flows is not constant either. The universe is not simply expanding. It is expanding at a rate that is itself changing, in a way nobody predicted and nobody fully understands. And the uncomfortable implication of the DZ result sitting next to the Hubble tension is that our model of cosmic time rests on assumptions about dark energy that may be wrong. If dark energy is evolving, the timeline shifts. Events we thought we had dated may have occurred at different moments. I think this gets underreported because it is too large to sensationalize cleanly. There is no single dramatic image. But the ground is moving, and if the engine of cosmic time is changing, that raises a question nobody in the field has a confident answer to. Changing toward what? So that is where the larger scale stands. Now let me bring it all the way back down to a set of machines that are running right now, tonight, while you are lying there. Because this story does not have an ending yet. It has instruments in the field. The atomic clock ensemble in space is operating aboard the International Space Station. It carries two clocks, Farao, a cold atom cesium clock developed by the French Space Agency, and a space hydrogen mailer built by Swiss institutions. Together they generate a time signal with a fractional frequency stability of 1 part in 10 to the 16th. At that level of precision, even very small departures from general relativity's predictions become visible. The clocks on the station are compared continuously against networks of atomic clocks on the ground through a microwave link that corrects for every known source of noise and drift. And what the mission is looking for is any departure from what Einstein's equations predict for how time should run at that altitude and that velocity. Not to confirm relativity. Relativity has been confirmed enough times. Nobody is spending a decade and a space station payload to prove Einstein right one more time. What they are looking for is where it fails, because everyone in the field knows that it must fail somewhere. General relativity and quantum mechanics cannot both be completely correct. We established that earlier, and it is not a controversial statement. General relativity needs time to be a dynamic physical thing that curves and stretches. Quantum mechanics needs time to be an inert external, given that does neither. Those are not different emphases. They are structurally incompatible descriptions of the same thing. At some level of precision, one of them has to show a crack. ACES is sensitive enough that if the crack exists at the scale physicists expect, it should be visible in the data. The results are still coming in. And what gets me about that, what really gets me, is the tense of the sentence. I want you to notice where you are right now. You're lying still, or nearly still, probably in the dark. It is quiet. Whatever this day held for you is finished. 400 kilometers above you, moving at something close to 8 kilometers a second, a cold atom cesium clock and a hydrogen maser are comparing themselves against clocks on the ground. Continuously, tonight, while you drift. They are looking for the place where Einstein's description of time stops holding. Nobody knows whether they will find it. Nobody knows which side of that crack we are on. Most people have no idea the experiment exists at all. It does not make the news, because there is nothing to report until there is something to report, and there may never be. But it is running, right now, above your head, while you lie there in the dark. There is something very calm about that, I think. Not urgent, just quietly extraordinary. That you happen to be alive at the exact moment when the most precise test of time ever conducted is being carried out, and the answer is not in. And ACES is not alone. In 2024 and 2025, multiple teams at the National Metrology Institute in Braunschweig, Germany, and at Giller in Boulder demonstrated working nuclear clocks based on thorium-229. The difference between these and conventional atomic clocks is not just precision, it is what is doing the oscillating. Atomic clocks use the transitions of electrons in the outer shells of atoms. Those electrons sit on the outside of the atom, exposed, interacting with the surrounding electromagnetic environment, and they can be disturbed by stray electric and magnetic fields. Every atomic clock ever built has had to fight that. Nuclear clocks use transitions inside the atomic nucleus itself, shielded from almost everything outside by the entire electron cloud surrounding it. It is the difference between a pendulum in an open courtyard and a pendulum in a sealed vault. The result is stability orders of magnitude better than atomic clocks, and sensitivity to effects that atomic clocks simply cannot reach. Specifically, sensitivity to changes in the strong nuclear force, the force holding protons and neutrons together. If the strong force has a coupling constant that varies even slightly over cosmological time, a nuclear clock will eventually detect it. And here is why that matters beyond the obvious, because it brings us right back around to where we started tonight. If the fundamental constants are changing, then the laws of physics are historical rather than eternal. They have a before and an after, which means they are inside time, and if the laws are inside time, then time cannot be derived from the laws. Something has gone in a circle. In physics, a circle usually means a missing piece. This particular circle has been sitting here for decades, and the nuclear clock is the first instrument precise enough to start looking for what fills it. What it finds, or does not find, will either close the circle or force us to redraw it entirely. There is one more experiment I want to tell you about, and it is the most audacious of the lot, because it does something nobody has ever done. What ACEs cannot do is test general relativity and quantum mechanics simultaneously, in a single measurement. Those two theories live at different scales, and every experiment before now has tested one or the other. Never both at once. That changed in July of 2025. Igor Pikovsky at Stevens Institute of Technology, Jacob Covey at the University of Illinois, and Johannes Beauregard at Harvard published a protocol that I find almost audacious in its ambition. Their design puts an atomic clock into a superposition of two different heights above the Earth's surface, the same clock, at the same moment, simultaneously higher and lower. In quantum mechanics, both are real. That is what superposition means. Not that we do not know which one, but that both are the case. In general relativity, those two heights correspond to two different rates of time flow. We established that in the very first experiments tonight. Higher means faster. So the clock in superposition is simultaneously experiencing two different rates of time, and the interference between those two time flows, the quantum signature of the superposition, can be measured. This has never been done because it requires quantum coherence and gravitational precision together at a level that only recently became technically feasible. But what makes it matter is not the precision. It is what the result is forced to include. Every experiment before this tested quantum mechanics in flat spacetime, or general relativity without quantum effects. This is the first protocol that makes both theories show up in the same number, at the same moment, in the same measurement. And if that number does not match what either theory predicts on its own, if the combined quantum gravitational behavior of time turns out to be something neither framework anticipated, then we will have direct experimental evidence that both of them are approximations to something we do not yet have. A theory without a name. A theory nobody has written down yet. What would it even look like? That is not a rhetorical question. It is the actual open problem, and it is what a significant fraction of theoretical physics has been trying to answer for a century. And while all of this runs, something quieter is happening in the background that I think is the most telling development of all. The international community is preparing to redefine the second. A coordinated comparison of optical clocks across 6 countries, published in June of 2025, was a major step toward making it formal sometime around 2030. The current definition, based on cesium oscillations in place since 1967, is being replaced with one based on optical transitions, oscillating at frequencies roughly 10,000 times higher, measurable with far greater resolution. Now here is what gets left out of nearly all the reporting on this. The redefinition is not just a technical upgrade, it is an admission that the previous ruler was not precise enough to measure the thing we're actually trying to understand. The new definition will allow physicists to test whether the fundamental constants drift, to probe the quantum gravitational behavior of time, to run experiments that the cesium standard simply could not support. But here is what I keep coming back to. Every definition of the second, the old one and the new one, is a definition of how time behaves, not what time is. The Standards Committee is not in the business of answering that. Nobody is. And there is something remarkable about rebuilding the ruler right now, at this particular moment. The new ruler will be precise enough to show us things we have never seen. Whether what it shows us will tell us what time actually is, or just hand us a more precise description of something we still do not understand, that is the question the redefinition process deliberately avoids. It may be the only question that matters, and I wonder sometimes whether the answer, when it comes, will look anything at all like what any of us are expecting. Part 13. The Circle That Does Not Close. If you try to follow all of these results to a single conclusion, the clock in Boulder, the stairwell at Harvard, the airplanes, the millimetre, the twins, the memory kernel, the billion to one, the superposed causal order, the equation with no time in it, the 2 photons, the wave that reflected backward, the machines running above your head tonight. What you run into is the same wall from every direction. Time is not what we thought it was, and the frameworks we have do not agree on what it actually is. So let me give you the disagreement honestly, because the disagreement is the real ending here, and I would be doing you a disservice to tidy it into something neater. Carlo Rovelli's answer, developed with Lee Smolin in loop quantum gravity since 1988, is that time is not a background. It is not a stage on which events occur. It is a description of how events are related to one another. Two events are related if one influences the other, if a signal can pass between them, if they share a causal connection. Time in this picture is nothing more than the ordering of those relations. It is not a thing, it is a description. And Rovelli makes a point that is easy to understand and quite hard to accept. When you remove the thermodynamic approximation, when you look at a small enough system, with few enough particles that statistical effects vanish, time disappears from the equations. There is no preferred direction, no flow, no before and after. Time, he argues, is what happens when you zoom out. When you have a large enough system with enough interacting parts that statistical behavior emerges and entropy starts to increase. Time is a macroscopic phenomenon, like temperature. I want to spend a moment on that comparison, because I think it is the single most useful idea in this entire video for making sense of what we have seen. Temperature does not exist for a single molecule. Ask what the temperature of one water molecule is, and the question is malformed. It has a velocity. It has a kinetic energy. It does not have a temperature, because temperature is not that kind of property. It is a measure of the average kinetic energy of a large collection of molecules. It exists at the level of the collection and nowhere else. And notice, heat flows from hot to cold, not because any law demands it, but because the statistics of large numbers overwhelmingly favour it. Remove the large numbers, go down to individual interactions, and heat loses its meaning entirely. Two molecules colliding are not exchanging heat. They are just colliding. Time, Rovelli argues, works exactly the same way. At the level of fundamental physics, in the equations describing individual quantum events and their relations, there is no time, no flow, no direction, no before and after. These emerge only when you zoom out, when you have enough interacting parts, enough entanglement, enough thermodynamic complexity that statistical behavior kicks in and entropy begins to increase. Time is what the universe looks like from the inside when it is big enough and complex enough to have a thermodynamic arrow, which means that asking what time is doing at the smallest scales, at the Planck length, at the level of individual quantum gravity events, is like asking what the temperature of a single proton is. The question may simply not apply. So, is time real? I think that is the wrong question, or at least an underspecified one. Temperature is real. It is measurable. It has genuine physical consequences. It burns you. It boils water. It drives engines. But it does not exist at the level of individual particles. So asking whether temperature is real is really asking whether collective emergent phenomena count as real. And the honest answer is that physics does not have a clean way to draw that line. Emergent is not the same word as fake. I want to be emphatic about that, because the loose version of this material gets repeated constantly, and the loose version is wrong. Nobody in this video is telling you that time is an illusion, or that it does not exist, or that your experience of it is a mistake. What they are telling you is something more precise and more interesting, that time may be the kind of thing that exists at one level of description, and not another, like temperature, like solidity, like the wetness of water, which no individual water molecule possesses. Now, Lee Smolin looks at the same data as Rovelli, the same experiments, the same equations, the same everything, and arrives at almost the opposite conclusion. And the fact that two serious physicists, who worked together for years and built a research program together, can sit with identical experimental results and reach incompatible positions is, I think, the most honest summary of where the field actually stands. Smolin's argument starts with a question that Rovelli's framework leaves unresolved. If the laws of physics are what they are simply because they are, if the constants and the equations are fixed, given from outside, not derived from anything deeper, then the universe requires an explanation that physics cannot provide. Where do the laws come from? Why these values and not others? The standard answer is that we measure them rather than derive them, which is true and which is exactly where we started tonight, in that laboratory in Boulder. Smolin finds that unsatisfying. His proposal is that the laws evolved, that the universe has a history not just of events, but of physical law itself. that the parameters of physics have changed over cosmic time, selected by something like natural selection acting on universes, with each black hole that forms possibly spawning a new universe with slightly different constants, and universes that produce more black holes, therefore reproducing more, so that the laws we live under are simply the laws that survived. I want to flag clearly that this specific mechanism is speculative, and Smolin himself flags it. It is a proposal, not a result. Nobody has tested it, and it is not obvious how anyone could. But the structural point underneath it does not depend on the mechanism being right. If the laws evolve, then time is prior to the laws. You cannot derive time from the laws if the laws are themselves products of time. Time would have to be the one thing that does not emerge from anything else, because everything else, including the rules, emerges from it. One says time is emergent. The other says time is fundamental. Both are reading the same experiments. I do not know who is right. I am not sure anyone does. And I find that fact, the genuine, unresolved nature of this disagreement between two people who have spent their careers on exactly this question, more interesting than any confident answer either of them could give me. David Albert's contribution to this picture is quieter than Rovelli's or Smolin's, and it cuts just as deep. He identifies what he calls the past hypothesis, the single assumption that does all the work in our experience of time. The assumption is this: the universe began in a state of extremely low entropy, extraordinarily, improbably, almost unimaginably low entropy, and from that starting point, entropy has been increasing ever since, not because any law requires it, as Boltzmann showed 130 years ago, but because there are overwhelmingly more high-entropy states than low-entropy ones, and random processes drift toward the more probable. That is the entire explanation for why you remember the past and not the future. Why causes precede effects. Why broken things do not spontaneously reassemble. Why time feels like it has a direction. All of it is downstream of one fact. The beginning was very ordered. Remove that one fact, keep everything else identical, and the arrow of time disappears. Past and future become indistinguishable. Memory becomes meaningless. Causality collapses. Albert calls it a hypothesis, rather than a law or a principle, because it is not derived from any deeper principle. It is an assumption we make because the evidence is consistent with it, not because any theory predicts it. And I find myself sitting with the strangeness of that for longer than is probably comfortable. Because what it means is that every experience you have ever had, every memory, every plan, every sense that there was a yesterday and there will be a tomorrow, is not grounded in a law of nature. It is grounded in a statistical accident at the beginning of everything, the directionality of your life, the feeling that time is carrying you somewhere. The entire structure of before and after that makes a human life coherent, that lets you have a childhood and a regret and a plan. All of it rests on one unexplained initial condition that nobody chose and nothing required. There have been serious attempts to explain that initial condition, and I want to give you two of them, because they fail in the same instructive way. Roger Penrose's answer is conformal cyclic cosmology. His proposal is that the Big Bang was not a beginning. It was a transition. In this framework, the universe passes through an infinite sequence of eons. Each eon starts with something like a Big Bang, and ends with something like a heat death, maximum entropy, cold, empty, dark. But here is where it gets strange, and where I have to admit the geometry is lovely. In the far future of an eon, when all matter has decayed and all black holes have evaporated, only massless particles remain, photons and gravitons moving at the speed of light. And massless particles do not experience time. They have no internal clock. The distinction between a nanosecond and a trillion years does not exist for them. At that point, Penrose argues, the universe loses track of scale. With nothing left that has a size or a duration, it cannot distinguish between very large and very small. And in that scaleless state, the cold, empty end of one eon and the hot, dense beginning of the next become geometrically equivalent. The heat death and the Big Bang are the same moment, seen from different sides. The end of time and the beginning of time are the same event, which means the low entropy beginning of our universe is not an accident requiring explanation. It is a mathematical consequence of the high entropy end of the previous one. I find this answer either deeply satisfying or deeply unsatisfying depending on the day. What I cannot do is dismiss it, because the geometry works. Stephen Hawking arrived at a similar dissolution from a completely different mathematical direction. Working with James Hartley in 1983, he proposed what they called the no-boundary condition, a way of describing the quantum state of the universe that does not require an initial condition at all. The approach uses a technique called a Wick rotation, which replaces real time with imaginary time, multiplying the time coordinate by the square root of -1. That sounds like a formal trick, and in most contexts it is. Hawking and Hartle argued it was more than that here. In imaginary time, the distinction between time and space disappears. The 4 dimensions of space-time become 4 spatial dimensions, all equivalent, none of them playing the special role that time plays in ordinary physics. And in that 4-dimensional geometry, there is no boundary, no edge, no point you can call the beginning. Just as the surface of the Earth has no edge, you can travel in any direction indefinitely and never reach a wall, never fall off. The universe in imaginary time has no beginning. The Big Bang, when you rotate back from imaginary time to real time, appears not as a moment where time started from zero, but as the point where a spatial geometry transitions into a space-time geometry. A smooth, rounded cap. Like the bottom of a sphere. Time did not begin there. It emerged there, from a region where the distinction between time and space did not yet apply. What I find remarkable about Penrose and Hawking together is that they are pointing at the same thing from opposite directions. Penrose says the beginning was the end of something else. Hawking says the beginning was a smooth geometric transition out of a timeless state. Both dissolve the question of what came before, but both of them assume something about time in order to explain time. Penrose needs eons to have a sequence. You cannot have a previous eon without a previous. Hawking needs imaginary time to transition into real time, and a transition is a temporal notion. Neither one escapes the circle. They push it back one step, which is not nothing, but it is not a solution either, and that brings us to the last idea of the night, and to the circle in its sharpest form. John Wheeler spent decades pushing a single idea that most of his colleagues found too strange to engage with seriously, and that the experiments of the last decade have made increasingly difficult to ignore. He called it from bit. The idea is that information is not a description of physical reality. It is what physical reality is made of, that every particle, every field, every physical quantity derives its existence from answers to yes or no questions, from binary choices, from bits. The universe is not a collection of things that can be described with information. It is a collection of information that we interpret as things. Stay with that for a moment, because it is easy to let it slide past as an interesting theoretical position without registering what it would mean if it were correct. If information is fundamental, if the universe is, at its deepest level, built from answers to questions, then the question of who or what is doing the asking is not a side issue. It is the central issue. A bit is not a bit in the absence of something that distinguishes between the two states. A yes or no question requires something that can ask it, which means Wheeler's framework does not just describe physics, it makes the existence of observers a necessary feature of reality, rather than an accidental one. And if observation is what generates the arrow of time, as the Oxford experiment showed, as Landauer's principle requires, as the quantum Zeno effect implies, then the observer is not a witness to time. The observer is part of what produces it. This is not mysticism, and I want to firewall that off very clearly before we finish, because there is a whole genre of confusion sitting adjacent to this material. Nothing in this video requires consciousness. Nothing here says that human awareness creates reality, or that the universe needs someone to be looking at it in order to exist. The Oxford result is thermodynamic. What was doing the work in that apparatus was a measurement device building a record and paying an entropy cost to do it. That device is not conscious. It is not alive. It does not need to be. It needs to be a physical system that retains information, and a rock retains information in its way, and so does a photographic plate, and so does a scratch on a wall. What follows from all of this is not that minds make the world. It is something stranger and more precise, that the arrow of time appears wherever a record is kept, and that keeping a record is a physical act with a physical price. But here is where I find myself genuinely uncertain in a way that I do not think is just a gap in my own understanding. Wheeler's picture raises a question about sequence that I cannot resolve. If observers produce time, if the arrow of time requires something that measures and records, then observers had to exist before time had a direction. But observers are physical systems. Physical systems exist in time. Something that exists in time cannot be prior to time. The logic circles back on itself at the exact moment it becomes most interesting, And I do not think that is a failure of the framework. I think it might be pointing at something about the relationship between time and observation that our current concepts are simply not equipped to describe. Wheeler himself asked the question in its sharpest form near the end of his life. Did the universe require observers in order to have a past? Not a future, a past. His delayed choice experiment suggested that the act of observation can, in a precise quantum mechanical sense, reach backward and determine how a particle behaved at an earlier moment. That the past in those experiments is not fixed until something in the present forces it to be fixed. Which means the past might not be a record of what happened. It might be a construction, assembled backward from the present, shaped by every act of observation that has ever occurred. So let me tell you where we actually are. Not where the textbooks say we are, where we actually are. We have built the most accurate clocks in the history of measurement, and they are telling us the constants of nature may not be constant. We have run experiments showing the arrow of time is not in the laws of physics, but in the act of observation. We have a mathematical description of the entire universe that contains no time variable at all. We have laboratory evidence that causality is not absolute, that quantum transitions have durations determined by geometry rather than by the flow of time, that a wave can be reflected at an engineered boundary in time. We have 2 independent measurements of the expansion rate of the universe, disagreeing by 5 sigma. We have a theoretical picture in which time emerges from thermodynamic complexity, and a competing picture in which time is the only fundamental thing, and both are consistent with all the available data. And we have an unsolved problem sitting at the centre of all of it, why the universe began in such an ordered state, that none of the frameworks can answer. What we do not have is a clear, consistent, experimentally confirmed account of what time is. I want to sit with that rather than move past it, because there is a way of hearing that sentence which makes it sound temporary. A gap in knowledge that will be closed by the next generation of experiments, the next theoretical breakthrough, the next decade of data from ACEs or from the nuclear clocks. Maybe it will be. I am not sure that is the right way to read where we are, because the deeper the experiments go, the more the question ramifies rather than converging. Every result that was supposed to clarify the nature of time has produced a new version of the puzzle. The more precisely we measure, the more precisely we can see that we do not understand what we are measuring. And here is what strikes me most, the thing I keep coming back to. The question of what time is has turned out to be the same question as what an observer is, and what information is, and what the past is, and what it means for something to exist rather than not exist. These are not separate questions that happen to be related. They appear to be one question, approached from different directions, which means the answer will not come from a better clock alone. It will require a new way of thinking about what physical reality is at the level where time and information and observation meet. We do not have that yet. We have pieces of it scattered across 130 years of experiment and theory, pointing in roughly the same direction without quite connecting. I do not know what that theory will look like when it arrives. I do not know whether it will dissolve the question the way Hawking and Penrose dissolved the question of what came before the Big Bang, by showing that the question was malformed, or whether it will answer it directly. I do not know whether time will turn out to be fundamental or emergent, real or relational, a river or heat or something we do not yet have a word for. But before we finish, I want to give you back 2 small things from earlier tonight, because they mean something different now than they did when you first heard them. The first is the arrow. The arrow is in the record, not in the electron. When we first said that, it was a summary of one apparatus in one laboratory in Oxford, a precise, contained technical statement about a double quantum dot. Now it is the whole problem, because the record has to be kept by something, and that something is a physical system, and physical systems exist in time. The sentence that seemed to explain the arrow turns out to be the sentence that traps it in a loop. And the second is your body. Your head is aging faster than your feet. When you first heard that, it was a curiosity, a small, charming, faintly unsettling fact about your anatomy, measured across a millimetre in Colorado. But you have been through Morava now, and Ravelli, and the twins, so hear it again. You do not have one time. Nobody does. Nothing does. The single shared present that you have assumed your entire life, the moment you thought you were in along with everyone you love, it was never there. What you have instead is a gradient, running the length of your own body, and a local now that belongs to you, and to nothing else in the universe. That is not a loss. I want to be clear about that. It is the most personal piece of physics I know. So here is where I leave you. Every experiment running right now, ACEs on the space station, the nuclear clocks in Braunschweig and in Boulder, the quantum network protocols being built in laboratories across 3 continents, is probing the same boundary from a different angle. The answer, if there is one, is somewhere in the data being collected tonight. Or it is somewhere in the data that will force us to ask a question we have not yet thought to ask. Physics ran an experiment on time itself. It ran 100 of them, across 67 years, in stairwells and on airplanes and in vacuum chambers and 400 kilometres above your head. And what came back was not an answer. What came back was a loop that physics cannot yet get out of with the concepts it currently has, that time appears wherever something is watching, and that the watcher is itself made of time. That is the disturbing result, not that time is fake, that the most careful question we know how to ask keeps returning us to the person asking it. The clocks are running, the numbers still do not add up, and somewhere in the gap between what the measurements show and what the theories predict, the actual nature of time is waiting, patient, entirely unbothered, and quite possibly the oldest thing there is to find. Whether we are close to finding it, or only just beginning to understand how far down the search goes, is the one thing not a single instrument on Earth can tell us tonight.